Electrolysis. So we're supposed to start with electrolysis. The very basics are first we need to talk about how or why things conduct electricity. Now, we do understand that metals are able to conduct electricity. And remember, in case of metals, they are able to conduct electricity because of their structure. And the structure is made up of lattice of positive ions surrounded by a sea of delocalized electrons, like you were answering yesterday for a question. And let me just clear that out. By a simple small diagram, we have all the ions, the positive ions of metal present in a proper layer form. They're very close to each other, but I'm drawing them a little bit far away intentionally on purpose, so as to make sure that you understand what I'm about to say. And then there are delocalized electrons that are surrounding the whole structure from the outside, inside, throughout the structures, in between the structure portions. Now, all these positive ions are capable of attracting these negative electrons, and these are delocalized electrons. By delocalized, I mean the electrons that got out of their valence shells, as metals like to lose electrons, and surrounding around the whole structure. Now, there are a number of electrostatic forces between these positive ions and their nearby delocalized electrons. As these delocalized electrons are free to move, so the metal is able to conduct electricity. Now, whenever something is able to conduct electricity, there should be some charged particles free to move. In case of metals, these are delocalized electrons that are free to move. Let's take a look with other substances. If we talk about ionic compounds, they're made up of ions, positive ions that are usually made when metals lose electrons, negative ions that are made when non-metals gain electron, but they do not conduct electricity when they're solid, because ions are very tightly held in position in the lattice and they're not able to move. They can only vibrate. That way they're not able to conduct electricity. However, when we heat them up, when we melt them, convert them into liquid, then the ions are free to move, so they can conduct electricity. Otherwise, if they're dissolved in water in aqueous solution, water is capable of breaking the lattice, the positive and negative ions, and water actually surrounds them, so they're free to move again. So in both the cases, when they're melted, converted into liquid form, or they're dissolved in water in aqueous solution, they're able to move freely. When that happens, they will carry the current and they will become conductors. Remember, anions are negative ions and cations are positive ions. These are the names that we give them properly. We're going to also study the same names in this chapter. Talking about covalent compounds, there are covalent compounds which do not conduct electricity in any state or solution. Covalent compounds consist of individual molecules. Now, those molecules are made up of mutual sharing of electrons. There is no loss of electron, there is no gain of electron. They don't have any overall charge. They don't have any charged particles to move around. All their electrons are held tightly and they don't even have delocalized electrons. So when they don't have any charged particles that can move around, they don't have any electrons that can move around, they're not able to conduct electricity in any state, be it the solid state, the molten state, whatever that state they are in. There are also some exceptions to this. Covalent compounds that form ions as they react with water. For example, ammonia, when reacting with water, forms ammonium ion and hydroxide ion. They can conduct electricity because those ions are free to move. In a similar way, hydrogen chloride gas dissolves in water to form hydrochloric acid. Now, this hydrochloric acid in water charges itself and ionizes to form hydrogen positive ion and chloride negative ions. That way, they are able to conduct electricity. So the example of ammonia capable of conducting electricity, or hydrogen with certain halogens capable of conducting electricity when dissolved in water, are the examples of covalent compounds which can conduct electricity. But remember, there are very few exceptions. For example, this, as we discussed, is an exception. This is an exception. This is an exception in water. This is an exception when dissolved in water. So these are the only exceptions that we can come up with. All right? Make sense?
Yes.
Okay, good. So passing electricity through compounds. When we pass electricity through metals, we don't notice anything. Maybe the metal gets a little hotter with a higher voltage, but that's about it. When you pass electricity through ionic compounds, either molten or in solution, a chemical reaction occurs. We came to know that in ionic compounds, either in molten state or in solution state, when electricity is passed through that, it brings about a chemical reaction, and to be a little bit precise, a decomposition reaction, a breakdown reaction. The compound was broken down into its constituents. So we started defining electrolysis as a chemical change caused by passing of an electric current through a compound, either in molten or in solution state. And we started calling those liquids or solutions as electrolytes. So yeah, we use this word, conductor, that's used for a solid, which can conduct electricity. Insulator is also a word that we use, again, that is also for solids. But if we're talking about liquids, we're going to use the same words, electrolyte or non-electrolyte. And these words are specific for liquids. Electrolytes which can conduct electricity and non-electrolyte which cannot conduct electricity. All right. So for this state, we use the word conductor and insulator. For this state, we're going to use the words electrolyte and non-electrolyte. Electrolyte is a liquid or a solution that can undergo electrolysis. Actually, when electricity is passed through it, it goes through a chemical reaction, a decomposition reaction to be precise, in which the movement of ions is responsible for the conduction of electricity, and they cause the chemical change to take place. If a liquid cannot conduct electricity, we call it a non-electrolyte. So we're going to use these words for this state of matter. We're going to use these words for this state of matter. The electricity is passed into and out of the electrolyte through two electrodes. Electrodes are actually carbon rods. Carbon is most frequently used for electrodes because it can conduct electricity. And by carbon, remember, here we mean graphite, because graphite is the only form of carbon that can conduct electricity. It is fairly inert. It does not react with most of the things. Platinum can also be used as a metal, being fairly inert, can be used instead of carbon. But the problem with platinum is that it is expensive. As platinum is expensive, and graphite is actually a pretty inexpensive alternative, that's why we prefer graphite. All right. So the positive electrode is called anode and negative electrode is called cathode. Remember, panic, positive electrode, anode, negative electrode, cathode. That's a good way to remember it. All right.
Okay.
These hints or these ways to remember stuff is pretty easy. However, we can do it like this. Anode is positively charged, anions are negatively charged. That's why they attract one another. Again, cathode is negatively charged and cations are positively charged. That's why they attract one another. This is another way to do it. We ask our students to go with one set, memorizing one set, and the other would be exact opposite. Don't try to memorize both sets at the same time, memorizing one of them and keeping the other one as the exact opposite works way better in exams. If you're good with memorizing all four at the same time, good, go ahead. Good with this first page? Shall we move to the next one?
Yes.
All right. Let's move on to the next page then. We're going to start with electrolysis of molten compounds first. Electrolysis of molten compounds is pretty easy. Let's take a look at the electrolysis apparatus first. We take a crucible, we fill it up with the compound, We heat it so much that it turns into a liquid. We call it the molten compound, the electrolyte in this case, because it's going to conduct electricity. We dip in both the carbon rods. We connect those carbon rods with the help of wires to a DC power supply. A battery would do good. We also add the bulb in the circuit. So if the bulb lights up, the whole circuit is complete and the current is passing through the electrolyte. So nothing at all happens until the lead to bromide melts. As soon as it does, the bulb lights up, showing that electrons are flowing through it. Now there would be some bubbling around the electrode, the anode, the positive one, that is connected to the positive side of the power source. And brown colored bromine gas is given off. Now a brown colored bromine gas is being given off at the positive electrode. Now, this side would give us a brown colored gas. So we'll have some bubbles on this side. You'll see some bubbles over here, right? Nothing seems to be happening at the electrode -1, but afterwards metallic lead is found underneath it. You will find some metallic lead over here or maybe some over here. When you stop heating, the lead to bromide solidifies again. Everything stops, there is no more bubbling, and the bulb goes out. This is the after part of the diagram. This is a very good part that shows the bubbles or the bromine gas and some molten lead over here. Sorry, I had a minor glitch in the internet. Continuing from the same part. So that what you can see on your left is actually the after part of the diagram. And in this part, you would notice that the bubbles and that brown gas all around the positive electrode. And at the bottom of the negative electrode, there is some molten lead. So this happens at the end of it. The power supply can be a 6-volt battery or a power pack. It doesn't matter which. The voltage isn't critical either. Now, what we tend to tell our students is that when we talk about the product at cathode, or when we talk about the product at anode, the good part with writing or the formula is that the first compound always goes to the cathode, and the second one goes to the anode. Or the way we write the formula, the first part always goes to the cathode, the second part always goes to the anode. So we'll have some lead around the cathode, we'll have some bromide around the anode, bromine gas, I mean. In this case, it's formed in the form of gas. So our molten compound broke down into its constituents, lead and bromine, which we got separately at separate electrodes, lead at cathode, bromine at anode. So it's going to happen in every single molten compound case. Let's say we're talking about NaCl, so Na would go to the cathode and the Cl would go to the anode. That's how we write the formula, and every single time with every single formula, the same thing is going to happen. The metal is always written first, always goes to the cathode. The non-metal is always written after, always goes to the anode. Why? Because metal forms the positive ion, which goes to the negative electrode, and the non-metal forms the negative ion, which goes to the positive electrode. Make sense?
Yes.
Great. Let's clear it up. Let's move forward. Now, explaining what's happening in it is pretty easy. I already explained that, but with the whole thing, let's go with it. Lead to bromide is an ionic compound. The solid consists of a giant lattice of ions, the positive lead ions, the negative bromide ions, and they're packed regularly. The ions are locked tightly in the lattice. They're not free to move. It does not conduct electricity, but as soon as it melts, the ions become free to move around, and that's the point when the electricity starts conducting. Now, in any power source, when you're going to connect to it, it pumps mobile electrons always from the left-hand electrode towards the right-hand one. This means there are extra electrons at the right-hand side. That's why it's negative. So what we say when we talk about a battery, the battery has extra electrons from the negative side, and it pumps those electrons from the negative side all the way to the positive side. That's what happens over here in any battery. The left-hand side is positive because some of the electrons have already been removed from it. The positive lead-2 ions in the molten lead-2 bromide are attracted to the negative electrode, as I explained earlier. And when they get there, each lead-2 ion picks up 2 electrons from the electrode and forms neutral lead. That's the equation over there. And it's pretty easy. We tell our students, no matter what the compound would be, no matter how many electrons it is short of, it would gain those number of electrons and it will become neutral at the negative electrode. That's what is going to happen at the negative electrode. We call it an ionic half equation. It's half equation because it's just the half of the story. It's only what's happening to the positive ions. With the negative ions, they're going to be a little bit different. The power source pumps new electron along the wire to replace the electrons that have been removed from the cathode, or we can say gained by this positive ion to become neutral. Now the bromide ions, being negative, are attracted to the positive electrode, just like what's happening over here. So the extra electron, when they get to the positive electrode, the extra electron which makes them negatively charged, move onto the electrode. This is because the electrode is already short of electrons, as we previously discussed. So for its side of the story, what happens is that they lose their extra electrons and they are converted into bromine atom. So bromide ion lost the extra electron to the electrode and became bromine atom. But bromine actually is very reactive, quickly reacts with another atom and forms bromine gas. That's why we had brown gas at that electrode. This is another half equation. So there are actually 2 half equations, one for cathode and one for anode. Half equations show either oxidation or reduction reactions. Cathode is reduction because electron is being added in the equation. Anode is oxidation because electrons are being taken out of the system. So oxidation is loss of electrons, reduction is gain of electrons, as we have defined them earlier. Good enough?
Yes.
As bromine quickly reacts and forms bromine molecule, so what we do is that we write its equation a little bit differently. So 2 bromine atoms are going to form a bromine molecule. So the overall equation is always written like this, that 2 bromide ions are converted into a bromine molecule after giving out 2 electrons to the electrode which required it. This happens over anode. The bromine atom has only 7 electrons in its outermost shell. Remember, the bromine atoms can mutually share the electrons to form a covalent bond. Both atoms have 8 electrons in their outermost shell. We say that the octet rule has been followed. It is really important to use the correct terms when we're talking about the reactions at electrodes. Bromide ions are attracted to the anode, where they lose electrons to form bromine molecules. So do not confuse bromide and bromine. Remember, bromide were the negatively charged ions, and bromine is a neutral molecule. All right? So that's how we name them. IDE for ions, like this one, and INE are actually for the molecules. Bromine, chlorine, iodine, like that. Bromide, chloride, iodide, like that. Right? So the names have their purposes. The new electrons on the electrode flow back to the power source. Because electrons are flowing in the external circuit, the bulb lights up. We sometimes talk about being discharged at these electrodes. Discharging an ion means that it is losing a charge. This happens either by giving up electrons in oxidation or receiving electrons in reduction. If you go on the previous page, you would find out that either at the cathode, the positive ion becomes neutral, or at the anode, negative ions becomes neutral. So we call it discharging. No ions remain in the ionic form. They are discharged to neutral portions, neutral particles. So the external circuit is the wire, the power pack, the bulb, and the electrodes. Electrons flow in the external circuit. The electrolyte is a collection of positive and negative ions. So ions flow in the internal circuit or the electrolyte. Okay. So I think we have already explained oxidation and reduction before, but let's explain it again. Oxidation and reduction actually comes from the fact that oxidation is loss of electron in terms of reactions, and reduction is gain of electron. An oil rig is the term used commonly to help the students. Oxidation is loss of electrons and reduction is gain of electrons. This term is pretty commonly used to ask the students to remember how to remember that what oxidation or reduction reactions are. All right, as defined over here, oxidation and reduction. Now, in our cases, what happened is that the reduction happened at the cathode and the oxidation happened at the anode. Right? Why? Because this is a gain of electron. The positive ions gained electrons to become neutral, so reduction. The negative ions lost their extra electrons to become neutral, hence oxidation. So lead-2 ions are reduced to lead atoms, and bromide ions are oxidized to bromine molecules. Make sense?
Yes.
Okay. Every time electrolysis happens, it's going to be a set of redox reactions. When I use the word redox, I mean reduction, oxidation occurring simultaneously. How is it occurring simultaneously? Because reduction would obviously be occurring at cathode most of the time, and oxidation would be occurring at the anode most of the time, and that would occur in the same time, hence the word simultaneous. We call these half equations. In every electrolysis, half equations are involved, so you'll be asked to write ionic half equations representing the reactions that are occurring at the electrodes. This is one of the most common questions of electrolysis. You're supposed to write the half equations for different substances. Let's say the next example we have is of NaCl. We're going to use molten NaCl. So it would be distributed into Na positive ions and Cl negative ions. So at cathode, Na positive ions gain the electron to become sodium, reduction. At anode, the chloride ions would be converted into chlorine molecules after the loss of electron, oxidation. Now, this is going to happen so many times that you would be clear and you would be confident that reduction always happens at cathode and oxidation always happens at anode. Reduction would mostly happen to the metal positive ions. The only exception is the hydrogen positive ion. Otherwise, it would be all positive metallic ions that are going to reduce at cathode. And you would only see the non-metallic ions getting oxidized at anode. All right. So most of the time, these are going to be metals, except for the exception of H positive, and most of the times these are going to be non-metals. So it's pretty obviously that you can connect cathode to reduction to metals, or maybe sometimes hydrogen, or anode to oxidation to nonmetals. Half equations must balance in the number of atoms on each side, but also in the number of charges on both sides. That's why in this equation, we need 2 electrons, as this 2 into -1, 2 multiplied by -1 is equal to -2. In the same way over here, 2 multiplied by -1 is equal to -2. So in the arrow, the left-hand side and the right-hand side have the same number of charges. That's what we need. We need the charges to balance one another. Either we need different charges to be present on the same side of the arrow, or we need same charges to be present on the different sides of the arrow to balance one another. These two cases are important. And you would notice that this is the case you see at anode, and this is the case you see at cathode. Take a look. Positive, negative. Right? So it should make sense that either two opposite charges on one side of the arrow or same charges on different sides of the arrow will balance the charges in a chemical reaction. And that's what we require with every half equation in electrolysis. Get the point?
Yes.
Good. We're going to clear it up. We're going to move forward. Let's take a look at another example. This time we're going with the example of Al2O3. Now, as soon as you look up in an example, you can either work with their group numbers to get their states, or you can otherwise go with the charges. This charge came from here, this charge came from here. So if aluminum had 3 charge and oxygen had 2, this is a metal, this must be the positive charge, this is a non-metal, this must be the negative charge. That's how you can come up with these charges to be used at cathode and to be used at anode. Get the point? Does it make sense?
Yes.
Good, good. Otherwise, if you think you can't work it like that, it's easy to notice an element and take a quick help from the periodic table. This is aluminum. Take help from the periodic table. It's present in group 3 of the periodic table, right? So you can work it out that its state must be +3. It has 3 electrons. It would lose those 3 electrons from a positive 3 ion. This positive 3 ion would be attracted to the negative electrode, so we can go for a reduction reaction for a metal at cathode. All right. So everything would make sense. As we had discussed, a cation goes for a reduction reaction. It's usually a metal ion, and it occurs at cathode. Now, in order to cancel out the +3 charge, we need to add 3 electrons, because a +3 charge would be balanced by 3 electrons. 3 into -1 is equal to -3. So a +3 and a -3 would balance each other out to give us the answer 0, neutral. And that's what is happening over here, right? And when we talk about this one, oxygen has, each oxide ion has a -2 charge. It is converted into oxygen atom, but oxygen atoms are too reactive and react to form oxygen gas. So we're supposed to balance this equation like that. Now this 2 into -2 is equal to -4. So we need to come up with 4 electrons out of it in order to balance it, because 4 into -1 would also be equal to -4. Also, if one oxide ion gives 2 electrons out, 2 oxide ions would give 4 electrons in total. And that's what's happening over here. Make sense?
Yes.
Good. then I'm also going to erase it and move forward. A common mistake is to put the electrons on the wrong side of half equation. Check the charges to make sure that you have same total charge on both sides. All right, so -4 on this side, -4 on this side is the total. If the total charge on both sides is same, then the oxidation reaction has been written correctly. For another example of zinc chloride, it's easier to work our way. This 2 must go here, there's a zinc over here, this must be 1. So zinc is 2, chloride is 1. My bad. So it's 1. So this must be positive, this must be negative, as this is a metal and this is a non-metal, right? So we take that +2, we add 2 electrons to it to neutralize it, or we can say that cancel out all the charges to give us a neutral atom. And we take that negative chloride ion, and there are actually 2 of them in order to balance out the chlorine molecule that it would give us. By giving out 2 electrons, an oxidation reaction at the same time. So if you electrolyze a molten ionic compound only containing 2 elements, you'll get the metal at the cathode because they form positive ions, and not metal at the anode because they form negative ions. I've already explained that. Reduction always occurs at cathode and oxidation always occurs at anode. I've explained that too. A good way of remembering that is an ox-red cat or an oil-rig cat. That means anode, oxidation, reduction, cathode. That's how we remember it. Cathode is the negative electrode, anode is the positive electrode. Cations are positive ions and anions are negative ions. I've explained that too already. So if it all makes sense, let's move forward. Moving on to the next page. Not all ionic compounds can be electrolyzed when they are molten. Some break up into simpler substances even before the melting point. For example, copper to carbonate breaks into copper to oxide and carbon dioxide even upon a gelatin heating. For example, this happens. So it's almost impossible to melt copper to carbonate because it decomposes even before melting. Which brings us to the second kind of electrolysis, electrolysis of aqueous solutions. If you can't melt something properly, we need to go with another substitute, another method that can get us through. Okay, so for aqueous solutions, when they are electrolyzed, the products are not same as molten solutions. So this is something what we need to practice. My bad. Let's get to the lab part first, how we go with the electrolysis of aqueous solutions. Afterwards, once we're done with how we perform it in the lab, we'll come to the chemical changes that happens in the background. Now, before we proceed with it, with sodium chloride, of course, it's going to produce some chlorine gas. So safety note, wear eye protection, do not smell chlorine, especially if you have asthma. Once chlorine is detected, the current must be switched off because chlorine is a poisonous gas and it can cause us problems. Like I asked yesterday, either we use a frame cupboard with reactions involving chlorine, or we go for doing this kind of experiment in a very ventilated space. The most ventilated place in the lab is probably the best one to carry out this kind of reactions. Now let's take a look. We have carbon electrodes, we have a rubber pump, we have a glass tube in which we have a concentrated sodium chloride solution. Remember, the concentration would matter. as soon as we go a little ahead, you would see that concentration matters a lot. And the products of concentrated solutions and dilute solutions are going to be different. We fill it up with concentrated sodium chloride solution. We take two inverted test tubes, which are inverted right on top of the carbon electrodes. So the test tube that is inverted upon the positive end of the carbon electrode actually has the anode-based product collection, and the one that has been inverted on top of the negative side has cathode-based collection. The positive and negative ends are connected to a battery with the help of wires. And of course, as we invert them, they are going to contain some of the concentrated solution. Now, the following procedure is used. We set up the apparatus, glass tube, rubber bunks, electrodes together. We all call it electrolytic cell. We pour some concentrated sodium chloride solution into the glass tube. We take test tubes and invert them up over every electrode. The test tubes must not completely cover the electrodes, or ions will be unable to flow and there will be no current. So you would notice that there is some space left over here, so that the current is properly carried out through the whole set of solution over here, over here. If they are brought all the way down and they touch the rubber bunk, that way they are not going to be completely conducting the electricity throughout the solution. Only some parts of it would conduct electricity, which will not be beneficial. Now connect the battery or the power pack to the electrodes. The experiment should be done in a fume hood, or when ventilated room, because chlorine gas is poisonous. I've already explained that. Now, when you see bubbles of a gas or metal forming in the electrodes, any gases can be tested. The test for gases are given in chapter 18. We're not going to work with that first, but when we see the bubbles of gas at both electrodes, we know that there are some gases forming at the positive and the negative electrode. However, what happens is that when we see the gases, we come to see that there are some bubbles of a pale green gas over here, and there are some bubbles of a colorless gas over here. We are getting to see that there is some hydrogen gas collected on the negative end of the battery, and on the positive end of the battery, there is some chlorine gas being collected, which has a pale green color. The observations, the visual observations are very important in electrolysis. We would expect to get the same volume of hydrogen as chlorine. However, in reality, we appear to obtain less chlorine than expected because chlorine is somewhat soluble in water. That's why, take a look, you would notice that there is a larger volume of hydrogen gas as it's insoluble in water, with small volume of chlorine gas because it's soluble in water. Make sense?
Yes.
Something that is not written over here, and I would like you to note, is that chlorine is not just soluble in water, it actually reacts with water to produce a couple of acids. We're familiar with this acid. However, there is another acid which it produces. That's why chlorine shows a small volume over here, because it mixes up with water and reacts with water and produces some acids over here, which we can later test with pH papers or stuff. As we haven't studied any pH papers or pH or topics related to it, that's why we don't tell this to students at this point. However, in Unit 2, you're going to learn the same thing and they're going to explain it to you properly. That happens in Unit 2. So for now, moving on, the electrolysis of sodium chloride solution. When molten sodium chloride was electrolyzed, the products at the electrodes were, we had chlorine at anode and sodium at cathode. But when you electrolyze sodium chloride solution, the concentrated solution, products are not the same. Although chlorine still forms at the anode, but hydrogen is produced at cathode. And this is different because we had sodium at cathode in the Molten's case. The hydrogen at cathode comes out from water. Now we need to understand that this time we have NaCl aqueous. This aqueous means water. Now we get Na positive ion from sodium chloride, Cl negative ion from sodium chloride, but water is also capable of breaking into ions. As astonishing as it may seem, water is a weak electrolyte. It ionizes very slightly to give hydrogen ions and hydroxide ions in this reaction. Although it's a covalent compound, but whenever electricity is passed through it, it ionizes slightly, as if it was an ionic compound, although it isn't. Now, there is a reversible sign in this arrow which shows that water molecules break up to form hydrogen and hydroxide ions, but these ions recombine again to form water. So whenever you have water present, you need to consider these ions as well in the system. So now we have two cations. Take a look. If we talk about cations, we actually have two sodium ions and hydrogen ions. If we talk about anions, we actually have two chloride ions and hydroxide ions. And remember, these two ions are coming from water. So no matter which ionic compound we are going to mix in water and electrolyze, these two ions will always be present over there along with another cation and another anion. So every time we're going to consider these ions as well when you're electrolyzing something in the form of an aqueous solution. Get the point?
Yes.
So let's take a look at it in detail. What happens at the cathode, what happens at the anode. Now, there are a couple of rules that we need to keep in mind before we discuss what happens at the cathode or what happens at the anode. Remember, if there are two cations, there must be one more reactive than the other. And the rule is that the more reactive one stays inside the system and the less reactive one goes to the respective electrode. And that's what they're going to tell you at this point. Let's understand the details. Now the system contains the two positive ions, the sodium ion and the hydrogen ion. Now they are both attracted to the negative electrode, cathode in this case. Sodium is a very reactive metal. This means it's very difficult to add an electron to sodium ion to convert it back to sodium atom. Hydrogen, however, is less reactive. It's easier to add an electron to hydrogen ion to form a hydrogen atom. So electrons are easily headed to hydrogen ions, which then form hydrogen atom. But hydrogen atoms are very reactive enough to react with another hydrogen atom to form a hydrogen molecule. So actually two hydrogen ions gain two electrons to form two atoms that combine to form a hydrogen molecule. Remember that hydrogen ions come from water molecules splitting up. So each time a water molecule ionizes, it also produces a hydroxide ion. So there is a buildup of these ions in the solution. Hydrogen ions and hydroxide ions. These hydroxide ions make the solution alkaline in the region around the cathode. Now, let's take a look what happens to these in the form of a proper equation. So water breaks up into hydrogen ions and hydroxide ions. Hydrogen ions are converted into hydrogen gas when they discharge around the cathode. However, there is a buildup of these ions around the cathode. There is an alternative way to look at the whole thing. We say that water gets reduced. Water gains two electrons from hydrogen gas and gives us 2 hydroxide ions. So now, what we explain our students is the same thing with many different methods. I'm going to go with these parts, these key points on the left to make sure that we explain every way possible. So the more reactive something is, the greater tendency it has to form an ion, which means the more reactive something is, the more difficult it is to turn it back into an atom. For positive ions, the lower the position of an element in the reactivity series, which we're going to study in chapter 14, the more easily it would accept an electron. Hydrogen easily accepts an electron. On the other hand, sodium ions do not accept electrons with the same ease. Because hydrogen ions are discharged from the solution in the form of hydrogen gas, they can no longer react with hydroxide ions and reform water. The ionization of water becomes a one-way process. That's why you see a single arrow and not a reversible arrow over here. Now, you might come across either half equation in the exam. Either should be accepted in answers. You may write this one or you may write this one. Both of them are acceptable in exams, and for both of them you get the complete marks. You can write whichever one you want. Let's discuss what happens at the anode. Now, there are again 2 ions, the chloride ions and the hydroxide ions, and both are attracted to the positive end. It's slightly easier to remove the hydroxide ions from the chloride ions, but there isn't much difference. There are, however, many more chloride ions present in the solution, so it is mainly these that are oxidized at the anode. So it really depends upon concentration. What the author is trying to say in the book is about concentration. So if we are using a concentrated solution, that means there are more chloride ions, they would be converted into chlorine. If we were to use a dilute solution, that means we have a higher concentration of hydroxide ions, so they will be processed and they will produce oxygen. How do they produce oxygen? This is by this equation. If sodium chloride solution is dilute, we have noticeable amount of hydroxide ions, then these will be the successive ones to get to the electrode. This would form water, but water was already a part of the system, so we don't really consider it as a product. However, they also form oxygen gas along with releasing some electrons in an oxidation reaction. So this is the equation that we use. How do we come up with this equation? It is very unlikely you'd be asked this question at this stage. Make sense?
Yes.
So let's say that we were successfully able to form hydrogen gas at cathode, and at anode we were successful in forming chlorine gas, which means we made it out of these ions and we made it out of these ions. Remember, we had these ions and these ions in the system as well. So let's talk about the remaining solution. So we had this ion and this ion left out. We have already used this at cathode and this at anode. So these 2 ions which are left in the system, they react with one another and they form something new, that is sodium hydroxide in the solution. So in case of electrolysis of solutions, what happens is that something forms at cathode, this one, a product forms at anode, this one, and another product forms in the remaining solution. So actually we have 3 products. Unlike what happened in the molten systems where we only had the product at cathode or anode, we have 3 products in the solution case. That's what makes the solution case a little bit more complicated than the molten one. Are we on the same page?
Yes.
So make sure when you're writing that in your exams, keep in mind, the molten system will only give products at cathode and anode, but the solutions are supposed to give you products at cathode, at anode, and there is always something left in the solution. So there might be a third product over there. Keep an open mind, keep a keen eye, and make all of your calculations. The best way to do that is to calculate from all of the ions. Like we were working with this. So we had this positive ion, this negative ion. From aqueous means water, we had this positive ion and we had this negative ion. So this goes to cathode, this goes to anode. So these two remain in solution, so they form a third product. So when you're working with solutions, make sure you note all four ions, the two positive ones and the two negative ones, and make sure you account for each and every single one of them so that you can correctly point out the three products we have in the system, right? And that's the best way to work for it. Note all four ions. After noting all four ions, note all three products, all three possible products, okay? So if we're clear with the first electrolysis of the solution, let's try another one. Electrolysis of copper to sulfate solution using inert electrodes such as graphite electrodes. Now, it's going to give us copper 2 ions from the salt and hydrogen ions from the water. Copper is below hydrogen in the reactivity series, which means it's easier to add electrons to copper 2 ions to convert them into atoms. So the cathode would be coated with the pink-brown copper. And here it's noted, this is pink-brown copper coated on the top of the cathode. The sulfate ions and the hydroxide ions, sulfate ions comes from the salt, hydroxide ions come from the water, would be attracted to anode. Sulfate ions aren't easy to oxidize. So hydroxide ions in turn oxidize and form oxygen at anode. Memorize this equation every time we're talking about anode. Most of the time this equation would come up, so it's better to memorize the equation. There is an alternative way of looking at the anode reaction. The water was converted into oxygen, gave us some hydrogen ions and some electrons. Of course, those hydrogen ions will be considered for either the cathode or maybe some other product can be at cathode and will keep the hydrogen ions for the system. That's why the solution becomes acidic, because there are too many hydrogen ions in the system. If the electrolysis is continued for the long ion, copper 2 ions will eventually be used up, so the color of solution fades from blue to light blue or even to colorless. All right? So in the end, let's talk about all the ions. So from copper sulfate, we got copper and we got sulfate. From water, we got hydrogen and hydroxide. Copper was given out at cathode, hydroxide was given out at anode. We are left with hydrogen ions and sulfate ions. Let me tell you, the hydrogen ions and the sulfate ions will react with one another to form sulfuric acid. And there is a dilute sulfuric acid solution left in the system. The reason that we keep stressing the use of inert electrodes is that what electrodes is made up of can sometimes affect the products you get. If you get copper electrodes, oxygen gas is not produced at anode, but rather the anode gets smaller because carbon of the anode reacts with oxygen and gives us carbon dioxide. So sometimes this oxygen may react with the anode material, graphite, and gives us carbon dioxide. In that case, the anode would get smaller. So sometimes the production of this oxygen gives a problem if we are using graphite anodes. Make sense?
Yes.
All right. So there are many things that a student needs to remember in terms of electrolysis chapter. So actually there is a lot of information, a lot of small knowledge pieces that you need to memorize. So keep marking, you might need to memorize a lot from this chapter. Up next is electrolysis of dilute sulfuric acid using inert electrodes. In this case, we only have one positive ions, and those are hydrogen ions, because the acid and the water gives the same kind of positive ions. So only they are discharged to give hydrogen gas. There are no other cations, so there would be no other products. At anode, as with the copper sulfate solution, sulfate ions and hydroxide ions from the water arrive. Sulfate ions are difficult to oxidize, so you'll get hydroxide ions giving you oxygen at this electrode. If you'd notice, you would see that there is twice as much as hydrogen than we get oxygen in this case. We're using inert platinum electrodes. Look at the half equations. For every 4 electrons that flow around the circuit, you would get 1 molecule of oxygen. But 4 electrons would produce 2 molecules of hydrogen. So that's why we have twice the molecules of hydrogen than that we have oxygen. Actually, if we look at the formula of water, we have twice the number of hydrogen atoms than we have oxygen. So it's easy that we'd get more oxygen gas than we do with more hydrogen gas than we do with oxygen. Actually, when we do this experiment, the amount of hydrogen we obtain is twice as much as oxygen. This is because oxygen is more soluble in water than hydrogen. Sometimes what we do to stop this happening is carry out the electrolysis experiment for a few minutes first in order to saturate the water with oxygen, and then we start to collect the gases. This gives much better results. However, the more the oxygen in the water, the better is the quality of that water for drinking. Remember, with more oxygen in the water gets sweeter and really gives a very good taste when we drink the same water. So, and how are we going to finalize that? So, electrolysis of some other solutions using inert electrodes. How are we going to work with that? In chapter 14, the reactivity series is given, so they have given the reactivity series over here for our ease. I'm going to work on this reactivity series for you so that it's easier for you to memorize the series. Remember, the students are supposed to memorize this reactivity series in the appropriate order. What comes first should come first, what comes second should come second, and you cannot change their position. So what I tell my student is that the whole series is made up of metals, but there are only 2 non-metals, and that's why they're written in brackets. So there is carbon over here, there is hydrogen over here, which divides the whole list into 3 parts. The top part, on top of carbon, these are reactive metals. The ones that are present in between carbon and hydrogen, these are moderately reactive. And the ones that are present beneath hydrogen are the least reactive metals. They seldomly react. All right? As water always gives us H positive ions, so I think everything has to compete with hydrogen. If everything has to compete with hydrogen, that's the position of hydrogen. So only there are 3 elements that are easier to reduce when it comes to comparison with hydrogen. All other are difficult to be reduced. So it's pretty easy that copper would reduce easily to give us copper atom, or the silver ions would reduce easily to give us silver atoms, or the gold ions would reduce easily to give us gold metal. Because these 3 are less reactive than hydrogen. So in case of solutions, these elements will never be produced at cathode. Instead, will always produce hydrogen. So only if these are present in our salts, they would produce out. Otherwise, in every single case, we're going to produce hydrogen. So that's why they say if the metal is high in the reactivity series, then you get hydrogen at cathode instead of the metal. So it's pretty easy. Most of the time we'll be producing hydrogen in the case of solutions. Coming to the second point, if the metal is below hydrogen in reactivity series, only then you obtain the metal at the cathode, and there are only three of them: copper, silver, gold. That's about it. These are their equations. All right. So this covers the cations part of almost all the possible solutions that we're going to face in our exams. If we talk about anions, we have this point. For anions, the solutions of halides, chlorides, bromides, or iodides, you obtain the halogen, chlorine, bromine, or iodine at anode. With all other common negative ions, sulfate, nitrate, hydroxide, carbonate, hydrogen carbonate, you always get oxygen from the hydroxide itself. And that's the equation that I have been asking you to memorize, that hydroxide ions would always give us oxygen as a product on anode. So there you go. That's the equation, and that's what you are supposed to memorize. This leaves the problem of a moderately reactive element such as zinc. Reasonable concentration can give you the metal, but dilute solutions will mainly give hydrogen. At this level, international IGCSE, you don't have to worry about these examples because they're not a part of exams. Even if they do, giving hydrogen out as a product will get you complete marks. Are we clear about these 3 points? Remember, these 3 points can help you out with almost any solution example out there in exams, no matter which unseen example they can come up with. So these 3 tips are the ones that you can use every time for solution electrolysis to get your answers right. So when we're going to practice past papers, I'm going to be constantly going through these 3 tips all the time, right? If that makes sense, I'm going to clear this up and we're going to move forward to the next page. Is it clear?
Yes.
I mean, okay, good. Let's move forward. So take a look at these rules. So we are going to go with potassium iodide aqueous or magnesium bromide or sulfuric acid or copper sulfate. Take a look. With all of these elements, as they do not consist of copper, silver, or gold in them, hydrogen is always produced at cathode. So that's the easiest part. Only in case of copper, copper is produced at cathode. So most of the time at cathode, if only it consists of these metals, they would be produced at cathode. Otherwise, the product is every time the same. The reaction is every time the same, and that's hydrogen. If we talk about anode, it's also easy. If it's a halogen like iodide or bromide, they would produce iodine or bromine. In all other cases, it would be oxygen with this same repeated equation every time. So most of the time at anode, oxygen is produced. Most of the time is at cathode, hydrogen is produced. Only in the case of these 3 metals is some other thing produced at cathode. Only in the case of these 3 halogens are they produced at anode. That's the only cases in which something else than hydrogen or oxygen is produced at cathode or anode, respectively. That's what last 3 points meant. When the last 3 points are written in writing, they seem to be difficult. But when we look at this table, we get a pretty good idea that how most of the time we end up with hydrogen at cathode and oxygen at anode. Make sense?
Yes.
Now, this table might have made the electrolysis of solutions a whole lot easier by giving you a complete mind map. But there are still a couple of points left to be discussed. So let's move on. What would happen with non-electrolytes? For electrolysis to work, there have to be some ions present so that they can flow through the system and the circuit is complete and the current passes on and we are able to perform the electrolysis. If you try to electrolyze a covalent compound, either molten or in solution, there would be no current flow. As there is no current flowing, the bulb won't lit up. There won't be any reactions. There won't be any electrolysis. All right. However, for covalent compounds, there have been exceptions. The ammonia solution and the acids are the ones that can conduct electricity. And I think performing this example of sulfuric acid already clears that up, right?
Yes.
Okay. Activity 6, quantitative electrolysis. The word quantitative means that we can always come up with a number to tell the amount of the product we are going to get at cathode or at anode. Quantitative means related to numbers. We can investigate it, how much product we're going to get in an electrolysis experiment. If we investigate the effect of changing of current on the amount of hydrogen we produce at cathode, in the electrolysis, we can easily work our way out with quantitative electrolysis. But we would also have to put a variable resistor and an ammeter in the circuit that can allow us to vary and measure the current. We'll also have to use a gas burette or a measuring cylinder to measure the volume of the gas produced. So on this side, we have a simple test tube. On this side, we have a proper gas burette with all the measurements given on top of it so that we can measure the amount of gas collected. This time we have added an ammeter and a variable resistor. The resistor, we can vary the resistance, and with ammeter, we can study the current that we have by varying the resistance increased or decreased. The rest of the structure is the same. Set up the apparatus, pour 50 cubic centimeter of concentrated sodium chloride solution to the glass tube, place the gas burettes as said earlier, turn on the power pack, connect it, and set the current to 0.2 amperes using the variable resistor, right? So after you do that, let's move on. Take an initial reading on the gas burette. We have to start the current flowing so that we can see what the current is. Therefore, we only can take a reading on gas burette after we have turned on the power. Start the timer. Take a notice of 5 minutes and stop the timer after that. Note the final reading on the gas burette. Repeat the current experiment for the currents of 0.4 ampere. Double the initial. 3 times the initial 0.6, 4 times the initial 0.8, and 5 times the initial 1 ampere. So we performed 5 different experiments to get more reliable results. Take a look. We started off with 0.2, had 7 cubic centimeter of gas, 0.40, 13.9, 0.6, 15.1, 0.8, 28, 1, and finally 34.9. These are our readings. The 0.60 gives an anomalous result, of course, that there must be something wrong with it. What's wrong with it, we can discuss a little later. We are going to discuss that a little later. However, if we look that up, that's the current reading. So it's near about the reading of 21. It should have been near about 21 or so, but it was around 15. We might have made a mistake with this one. We're going to discuss that a little later. This graph gives us a very good idea that it's a straight line. Because current is a continuous data, we draw a line of the best fit graph through the points. The reading at 0.6 there is anomalous point, means odd out of the whole thing. We do not include this when drawing our line of best fit. The reading at 0.6 ampere is too low, and it could have occurred because the current we used was too low, or some of the gas escaped out of the burette that we weren't able to check. The line of best fit is a straight line and goes through the region. We can say we have a proportional relationship, which means more the amount of the current, more would be the volume of gas produced, and vice versa. Get the point? So the amount of current and the volume of gas produced are directly related to one another. And that's here we finish the chapter.